Hi back. The next and actually last talk for today, so no pressure. Is David here? So, and he will talk about Rack and Ruby, I guess. So, give a warm welcome to David.
Hello. Okay, I can hear myself. Great. So, does anyone seen this talk already? The people who've seen this talk, did they vote for it? Okay, weird. So, as they said, I'm David, and I'm going to talk about how to hijack proxy and smuggle sockets with Rack and Ruby. So, yesterday, I realized Hamburg is great. This was my first time here. Unconf is like Basecamp. I learned this. So I was like, what's Basecamp? And someone said Basecamp is like Unconf. I learned about fishbowl discussions. Before they explained it to me, I thought about something like this. And I had a nice discussion during the first talk with one of the organizers. I also like to live dangerously, so I prepared your live demo, which I will run just now. So, Vagrant, is it visible? Yes. Okay, so I'm going to start a Vagrant box. It will download stuff in the background, so please no torrenting and stuff, because then the talk will be longer. In the end of the talk, it will all make sense, so let's start it. Sorry. Yeah, so as I said, I like to live dangerously. It's really bad to do a talk after such party yesterday. I borrowed too much happiness from the future and I'm paying the interest right now. Today, I'm a little uncomfortable because of that. You know why. This is the last talk, come on people. So, I'm from the Hungarian-speaking part of Slovakia, and I came here from the Czech Republic where I live, from a town called Brno, which is famous for beer, MotoGP, and we had a genetic experiment 150 years ago. Not this, but Gregor Johann Mendel did the famous pea experiment in the town of Brno. So that's where the town is famous from. I worked for a small company called Red Hat. This is the new logo, deal with it. On the project called ManageIQ, which is an application, a Rails-based application to manage your cloud. So if you have a cloud, we can manage it. It's open source, of course. And one of the things I'm working on are called remote desktop session. If someone doesn't know what remote desktop session is, you probably used Windows, right? There's this thing in Windows where you can connect to a computer and take over the control, and if you write the right password, it will get you and you can remote control the desktop. So we are kind of working on in-browser remote consoles, which are like remote desktop sessions, but inside the browser, surprisingly. They look like this. So we have an HTML canvas, we connect to a remote endpoint, and you have inside the browser window a whole full feature desktop environment. In our project, it looks like that. So you have a button to access a VM console that opens a pop-up window where you have your desktop. And if you look at the architecture, if we look at the architecture of this thing, you have a virtual machine somewhere. We manage cloud, so obviously. It runs on a hypervisor. This hypervisor exposes a remote desktop protocol. Let's say VNC. It can be others, but for the simplification, I will just talk about one. We support like 5 or 6. So the browser doesn't really speak VNC, and the closest thing to VNC is maybe WebSockets. It's a bidirectional communication. And you need something in the middle, something to bridge those two endpoints together. Let's name it the proxy. So we are at the first chapter from the title, the proxy. If we look into this proxy from closer, we realize that it consists a lot of scary stuff like fibers, sockets, concurrency, networking, we were gonna all cover those. So from a different aspect, you have two endpoints. One of them is the WebSocket, the other one is the VNC. You need to read stuff from the WebSocket endpoint and write stuff to the VNC endpoint and do some translation between the two languages. So if I talk about endpoints, let's uncover them. They're basically sockets. I did this joke in Australia, they didn't get it. So when you use Ruby, you write sockets like this. So here I'm connecting to, okay, the website is, I forgot to update it, I'm sorry for that. So I'm connecting to port 80, which is HTTP. Then I send a request with writing, then reading back. I get back some headers and some payload. This is an HTTP request. And if you look at the methods, read, write, close, what's the thing that comes to your mind, other thing than sockets? Yes, files. So sockets are basically like files, but for networking. With a little twist, but we will cover that. So if you write to a socket, you actually write to a buffer, like this. And when there is time on the network and the network card, the operating system takes this data and forms packets and sends it to the network card. Do you know what happens if the buffer gets full and you want to write further? Okay, so I see faces that you don't. So if you write, I wasn't prepared for that, sorry. So if a thing happens called blocking, so your write operation will wait until you have time for writing into that buffer, so the write operation can take even minutes. This is not really good because you could do useful stuff instead of waiting. The reading works the same way, but I was lazy to make the animations for that, so you have to use your imagination. In the opposite sense, you are waiting for something to appear in the buffer, and if it's nothing, there is nothing there, you wait until something appears, and that's called blocking transmission. And if you want to do the proxy with this kind of transmission, you have to write something like this. So you have two sockets, one for the VNC, one for the WebSocket, and you need to read from both, translate with this magic method I have in the middle, and write to the other side. The two loops, threads are symmetric. Basically, you need to do the transmission unendingly until one of the connection ends. This is not really good because if you have like 500 connection, you need 1,000 threads, and Ruby isn't really strong in that. There is a solution for that called non-blocking I/O. So instead of read, write, you can use read non-block, write non-block. These methods aren't waiting. If there is nothing in the buffer for reading, you just get an error, E will block or E again, depending on the context. Or if you write and there is no space in the buffer, you get the same error. Basically, the readiness testing, the waiting is extracted out to a separate call into IO select, which takes 3 arguments and a timeout as an input. So you push 3 arguments for an array of sockets for reading, writing, and errors, and this select will wait until something becomes ready. The timeout can be infinite, but you just, in my cases, I just set it to 1 second, and I have an endless loop. So if you use select, it's something like this. I mark the IO select here. So this is a really simple class where you have a background thread with the event loop method, where you just test sockets for reading, and then whatever comes up, you iterate through the ready sockets and read the stuff from it. Does this make sense? Okay. So it's really good if you have one directional transfer, but if you have if you want to read from one socket and write to the other, you have the problem of dependencies. A needs to be ready to read, and B needs to be ready to write. And you cannot really do this easily with a single IO select. So let's say we have the 2 sockets, socket A and socket B. They are mapped to each other. So one of them is the VNC, the other is the WebSocket. I have some methods for the translation. And what happens if we do IO select on this? We iterate through the ready sockets, do the translation, and do the transmission afterwards. This code can cause a deadlock in these two lines. If socket A is ready only for reading and not writing, and socket B isn't ready for reading or writing, then the IO select will return a single element array into the RDS reads variable, socket A, and the writes array will be empty because nothing's ready for writing. So you get into this loop and you hit the next line, this one, because the writes is empty. This is highly probable. So if you look at it, the next iteration of the loop will also return the socket A, but socket B isn't ready, so you end up with a spin lock where your process isn't doing anything. You're just eating 100% of CPU. This is really bad. We use this in production, of course. I was looking into alternative solutions, like quitting my job or not using Ruby. It ate up like a year of thinking about this, how to solve this effectively. So one option was using threads with blocking I/O, which isn't really good because the GVL, you don't really want to run 500 or 1,000 threads for half of the number of connections. You can use some kind of libraries for asynchronous I/O. Celluloid and Event Machine are great. Unfortunately, we're using Postgres in an async version where those things are failing. The async library is awesome. I really suggest it, but when I was solving this problem, it didn't exist. So we wouldn't have this talk if I would know async. I would just use it right now. Or I was looking also into the promise of Ruby 3 autofibers, where fibers automatically yield when you call IO wait, very similarly to how the crystal works. They would be really awesome to have. Something like this. So you define them like threads, you do blocking operation, and some kind of magic transforms it into non-blocking communication, which is inside the Ruby VM. Problem with this is that it's coming in Ruby 3. So me and my colleague came up with the idea of bouncing select. And the whole secret about this is to have the arrays, which you call in IO select dynamic. So here is the same code with adjusted things. So here are the dynamic arrays. You see 2 read and 2 writes are dynamic. And anytime you call an IO select, you remove the ready sockets from these arrays. And after the transmission, you push it back on the end. Okay, I'm not blocking it. So when we have the same case study, when socket A is ready, only for reading, the second red marked part will remove this socket A from the array. We will hit the next, we'll get out from the loop, and the IO select to read doesn't contain the socket A anymore, so you don't end up with a spin lock. So you're basically dynamically editing the array of sockets. This is still not ideal, because anytime you call IO select, you need to push all those sockets to the kernel, and it takes time to copy all the data. So if you have like 500 socket descriptors, you need to copy all that stuff into the kernel space memory, and it takes time. So I was looking into alternatives. I found EPOL. It basically splits up the registering the socket and waiting for the socket into 2 operations. So you copy the socket only once into a permanent structure, and you ask in a separate call to wait for its readiness. It's not available on anything else than Linux, so sorry for the Mac users. There is an alternative for BSD that works on Mac in KQ. If anyone wants to implement it, feel free to do that. I don't have a Mac. For now, I'm just using a fallback to the normal IO select if you're using a Mac. Our stuff runs on Linux in production, so we don't really care. And the really cool thing about EPOL is it does one operation for us for free. So there is a flag called EPOL one-shot, and if you register a socket with EPOL one-shot into the EPOL internal structure, after the socket becomes ready for reading or writing, it gets removed automatically. So basically, you don't do the second red marked thing, it's done for free for you. So I had to write some C code for it, for registering for EPOL. Those are snippets from our code base. everyone understands C, right? So it's basically the select call is calling equal weight, and then we iterate through the result of the equal weight and edit a Ruby structure that's easy to read, and we can work with it together. This thing works well on Linux, and we fall back to IOSelect for everything else. If you would like to write some support for OS X or FreeBSD with KQ, feel free to open a pull request. I will be really happy to merge it if it doesn't have any memory leaks. So let's go to the second part, WebSockets. So WebSockets are bidirectional connections built on top of HTTP. So instead of using the request response model, you ask the server to upgrade from HTTP to something else with a handshake. So you have your browser and web server. You send a request with this connection upgrade and upgrade WebSocket headers. The server says to, yeah, I can speak WebSocket with you. So now we will speak WebSockets. So you change the protocol type during runtime. So you open one connection and it ends up being something else. It's really awesome. So if we look at rec, the Ruby server middleware, sorry. So the Ruby server middleware is a request response server. It works really simple. You define a lambda or a function or an object that responds to call, and you return with 3 elements. A number, which is the status, a hash with all the HTTP response headers, and the body, an array which contains the body of your website. This is a hello world example from the rec website. It just writes you hello world to any HTTP request. Basically, anytime you open a website, it calls a function. So it's a function as a server. Anyway, this doesn't really work well for like more longer open connections, because then you will get stuck in that function call and you're using resources. So the developers of rec came up with socket hijacking, which is basically to ask kindly the WebSocket, the rec server to give you the socket and handle it, and you would handle it. You would be responsible for the socket instead of rec doing that. I'm not sure if you know this movie. He's saying hijack, and he thinks that he says hijack, and this happens. That was the first thing I found for hijacking. So this is how it looks like. This is a really simple rec server. You have a proxy which runs in the background somewhere. You have to write it. I have some testing, and the important part is this. This is the hijack. It returns you the socket. Then you can do some magic, which gets you an address and a port. With that, you can connect to a remote endpoint, the socket VNC, and push those things to the proxy. And then you return with something dummy, so the rec will not complain about stuff. It happens in a few seconds, let's say, instead of a long-running connection. So this proxy will handle the connection for you instead. So basically, you take away the socket from rec. This is how our stuff works, this thing. So I was promising some kind of smuggling and crazy stuff. So when I was looking into HTTP upgrade, I was thinking about what if we would upgrade to something else? Would it work? And I started playing around, and the answer is yes, it works. So I started to think, and I wanted to change the original architecture a little. With this trick, you would be able to run a regular VNC desktop client's connection through a client proxy, through HTTP, to a remote proxy, where it gets converted back to VNC and gets to your VM, which is kind of crazy, right? So you would ask me, why would I do this? So the experience of a remote console, at least for some of our customers, isn't that smooth. So you don't have a clipboard, you don't have key mapping, and it's not really comfortable to work with HTML5 canvas because it's kind of slow. So it's basically the war of browser versus desktop. A desktop application is always faster. Also, it's more comfortable to SSH, not just VNC, but you can do other protocols. So it's more comfortable to SSH from your own favorite terminal than through the news browser window with where your keyboard shortcuts doesn't really work. So back to this thing. As you know, there are two hard problems in computer science. One of them is cache invalidation. The other one is naming things. So I came up with a name. You've probably seen it somewhere. So as you all guessed, it stands for Protocol Upgrade Raw Request. And it's basically HTTP upgrade or downgrade to VNC or SSH or any kind of other protocol. It's basically TCP smuggled through an HTTP connection. And with our product, I'm planning to do it like this. So here is our architecture. There is a cluster with overt R stuff, manage IQ running with a web server, a proxy included. And the client with the browser wants to access the VM. So clicks on our screen to access a native console. This fires a request to the web server with some message, I haven't figured it out yet. And the web server says back a message, I haven't figured out it yet. The browser activates a browser plugin to that address he got. The browser plugin says that it's listening on localhost some random port, and the browser displays some information about where to point your desktop client. Let's say localhost 1234. Then you open your desktop client and point it to localhost 1234. It goes to the plugin. The plugin opens a connection to the web server, which is getting routed inside the REC middleware to the proxy with the HTTP upgrade to PER. The proxy sends back an HTTP 101. Then you have a PER connection, which is basically a VNC connection, but with HTTP handshake before. The proxy sends further a VNC request, and through this nice blue line, I hope it's visible, you have a tunnel to your VM through an HTTP connection, bypassing any firewall rules, just basically on your own environment where you have only HTTP open. I lied. So the plugin isn't that simple. You cannot really open a TCP port. It's not that. Or maybe. So the browser cannot really open a TCP port, not even a plugin for now. So you have to use a native library, which is possible right now, both with Chrome and Firefox. But there is actually a draft for opening, like asking your permission from the browser to the user to open any kind of TCP port on your computer. So as you would, your browser wants to access to the web camera, there is a draft in the new web standards to open a TCP port. That's coming soon, then you wouldn't need any kind of plugin. So I have this architecture for now. Server, I was just explaining it. The plugin also, so it uses native messaging. That's the trick that opens a binary. The binary for now is written in Go because that's a really concurrent language and you can compile it on Windows too. So this thing works on Windows with a client. And I still need a front-end library. I haven't figured it out. So anyone who likes JavaScript, it's open source, pull requests welcome. I can show you how the server looks like. It's really similar to REC, and it's actually a web application, so you can put it into your Rails middleware. So you implement just your magic function that will get from the environment, so the URL or cookies or whatever, the host and the port where you want to connect your client. And that's all. It behaves like HTTP, so it has all the advantages or disadvantages of HTTP. You can use middlewares for authentication, logging, routing, whatever, cookies, headers. You can use HTTPS, so it can be secure. And for now, it needs both the plugin and the library. It's really far from being production ready, but it works, and I can prove it. So I really hope that the live demo actually worked out. I have 6 minutes. That's more than enough. Yes. So here the thing is running. So I'm going to show you what this Vagrant built. So you see it? Should I zoom it more? Okay. You don't see it, or should I shouldn't zoom more because you were like. Anyway, so I installed Docker and some basic packages. Then ignore this line. I pull down 2 containers. One of them is an XSCF VNC server, so it's a desktop environment in a container, and an SSH server that might not work. Okay. So an SSH server and a VNC server. I don't expose any ports on the Docker container, so it's running on a VM, running in a container, so my computer has no access to these containers, only the VM. On the VM, I'm installing Purrr and Puma, and in Puma, I've set up some aliases for the addresses, and I'm starting this Vagrant server SH, which is a shell script, so it just runs Puma with Purrr. I have this Purrr server, which has some static routes to index.html, and based on the request URL, if the URL is VNC, it forwards my request to VNC server, which is one of the containers, or SSH servers, which is the other containers, and we run this app. The index file looks like this. So it's some crazy JavaScript that actually communicates with the plugin, the browser plugin. It basically dispatches a Purrr request event with opening a URL, and this URL comes from the start function. It starts VNC or SSH based on which button I will click. So if I run the server, open the VM address. Yeah, this is the thing you shouldn't see. No, load localhost. Bad habit. So I have this nice demo, so I'm going to trigger Purrr. The browser plugin is installed here. Is the cat, if you don't see it. This cat. So I hit start VNC. It opens localhost something. And I have prepared, no, I don't have, a remote desktop connection. I just open this localhost port. I really hope it will work. Usually does. No. Okay, let's retry it. Sometimes it happens, like this is the second time it doesn't work. Yeah, so the password is demo. So I'm on a VNC connection, which is running through an HTTP browser plugin, and if you're questioning the performance of this thing, so I'm pretty sure it's German, it will be an advertisement. No. So yeah, this thing goes through a VNC connection that is tunneled through an HTTP Rails web server, and it's tunneled back to the container where it's actually running. And if I hit the stop button here, it actually closes the connection. So thank you very much. If anyone wants to ask questions, I have those stickers with me. You can find me there. Thanks.